In this video, we will give a correctness proof of the parallel 3D fast Fourier transform algorithm. We will show that the algorithm will do what it has to do. So the proof of the correctness of the algorithm for the parallel 3D FFT algorithm is as follows. So let's look first at superstep 0. And let's look at the first part, which does just a local fast Fourier transform. Let's call yk of ys of k. That's this transform. So we take, with a short notation, j in n over p, meaning j1 and n1 over p1, j2, etc. We have the input, the xs, the local part of the array, k, times, by the definition, omega n1 to the power j1 k1 times omega n2 j2 k2, and then omega n3 j3 k3. What we will do, by the way, is we'll give, in every phase, we'll give a different letter, x, y, z, w, v, so that in the end we can relate v to the original x. So we'll do it step by step, and we'll compute what y is in terms of the original x, z, etc. And then in the end, we'll hope to get to the formula for the multidimensional FFT. And that shows that we have achieved what we wanted to achieve. So this is the first step. It's easy. Then we look at superstep 0b. And for this, we need, this, by the way, it was length n1 over p1, n2 over p2, n3 over p3. So we want to look at what these omegas are, and the omega of n over p to the power jk, for example, for j1, k1, we can write that this is e to the power minus 2 pi I divided by n over p times jk. And you see that we can move the p upstairs, e to the minus 2 pi I divided by n jkp. And this is omega n to the power jkp. So that's one way of rewriting it. And then the twiddle, you multiply by an omega n to the power, what is it, sk. So the twiddle is multiplying by this omega n1 to the power s1, k1, etc. So this is happening here. And then we get a result, which we will call then zsk. It's the sum over all the j's xsk. And then I write this as omega n1, and the p1 moves upstairs, j1, k1, p1, plus, and that's the twiddle, s1, k1, same omega n1. And then, of course, you see a k1 here and a k1 there. So we can take this out of the brackets. So what we do here is J1P1 plus S1 times K1. And we have the same for omega N2, same for 2 and 3. I will be lazy and not always write this, but the same expression we get here. So that concludes superstep 0. We have a z expressed as the original x.
So for the communication superstep, let's just first remind ourselves what this was. We put the arf strided subvector with stride p in PR as W R, and then the as the S chunk, so S times n over p squared up to S plus 1 times n over p squared minus 1. So now we work our way backwards. And we are going to do FFTs on subarrays with stride n over p squared. So let's look at one of these arrays and take component S prime. Now this is equal to just WR and then T plus S prime times this stride times n over p squared, of course. And we can now also see this as a block distribution where we just take a contiguous subarray, namely S prime times n over p squared up to S prime plus 1 times n over p squared. And then our component is just t. So now we are going to use this line over here. So that means that this component is equal to z of, and now our processor index is going to be the s here, so the s prime, of r p n over p, and then component t, which is in other words equal to zs prime. And then we start at r and we take t steps of stride p, so r plus t times p. And now we can use our results from superstep 1 to fill in here what this is. And that means we get the sum of j in n over p of x s prime. And now our index is not k, but r plus t times p. And our vectors are going to be n1, and then j1 p1 plus s1 prime multiplied by this expression here, which is r plus tp. And then, of course, the same for the twiddle vectors in the second and third dimension. And then, of course, we also need to take the indices here.
Okay, A reminder of the last superstep, superstep 2, is we perform a three-dimensional Fourier transform of small length, p1 in the first direction, p2 in the second, and p3 in the third direction on the local part of the array. And it's W now with the lettering that the letters that we gave them. To finish off with the last superstep, we take the result of the previous superstep, but please note we made an error here. The index of the xs prime should simply be the j, like we have here. So that is important. And then superstep 2 transforms w into v by performing a three-dimensional Fourier transform of small length, p1 in dimension 1, p2 in dimension 2, p3 in dimension 3. So we are going to look at what this v is for a particular element, t plus k times the stride. And then we substitute, first of all, the definition of what a three-dimensional f of t does. We take a sum over all the j's. In this case, actually, it's not the j's, but we'll use it because that's an index that we've already used. We index over all the p's. So we take an S1 between 0 and P1 minus 1, and etc. So we take as our index S prime, and then we have this element, and then, of course, the component S times the omegas. So we have component S prime, of course. S, that's the part, that's me as a processor. So component S prime times the omegas. And the omega then that we have, the first direction is omega with P1 as length, because we're doing a f of t of length P1. And then we have here S1 prime times K1, because we're talking about component K of the final output. So this is the definition of the one-dimensional transform. And of course, we also have omegas for P2 and P3. And this we can write differently as the sum of S prime element P. And then this, we have seen in the previous superstep what it really means. So the S prime component is a sum. The sum of J in N over P, XS prime with the corrected J that we have here. And then we get a long term, we'll just copy it, omega N1 to the power J1 P1 plus S1 prime, S1 plus T1 P1, and then we have an omega P1 to the power S1 prime K1.
So now first we are going to take these two vectors together, and we're also going to manipulate it a little bit to make it easier in the next steps. So what we can do is we can take the p root of unity to the power of S prime k, and then transform this into the nth root of unity. And then we have to multiply by n1 over p1. So we can add something in the exponent as long as it's a multiple of n. So what we're going to do is, because we want to get an expression like this over here, we're going to say j1 p1 plus s1 prime times k1 times n1 over p1. And now we have introduced an extra term, which is j1 p1 k1 n1 over p1. and that is a multiple of n. So, so this is fine because the nth root of unity to the power of n is equal to 1. So now we can take this sum together, and that means I will write this on a new line because it's going to become a very long exponent. That we get omega to the power of n1, then this factor which we can take out, and then we are going to get s1 plus t1p1 from this, and then we also have to add this. Plus k1 I will erase this thing over here. So this is going to become our new factor. And of course we have to do this for the second and third dimension as well. Okay, so now we are going from the parallel view from processor S to just the global view. So that means that we just get V of P times T plus K times N over P squared plus S. And this is equal to the same expression over here. S prime in P, J in N over P. And now for X we are also going to the global view, so that means we get X of J P plus S prime multiplied by this thing again. And now we are going to get rid of this double summation by noticing that the product of these index sets is really just the same as taking one index which is smaller than n, and the index transformation is given by S prime J mapping to JP plus S prime, which is also conveniently the thing that occurs here everywhere. So I would just wipe this out and use this index transformation, which means we only have one sum here. And as a index I will use J prime. That means that this index is just going to become J prime. And then the coordinate, the factor is going to become, just grab a different pen, omega n1. And then the exponent is going to become a J prime times S1 plus T1 P1 plus K1 and 1 over P1. And you can see that this is the definition of the Fourier transform, because we have the J prime from the sum, and then this whole thing is this index, and that means that we have concluded the proof.